morning, people. I hope you're doing well, my lovelies. So at long last, let's take a look at something that may contain science. Perhaps up to 5 sciences. 1 for each purported fundamental force in our universe. Sam, no. There are 4 fundamental forces in my textbook, and, well, yes. And that is thanks to the standard model of particle physics. But if you've been hearing rumors recently about a 5th fundamental force, it's thanks to recent work reported at a seminar hosted by Fermilab. And that's cool. But, what the heck is going on? Well, it's all part of the scientific back and forth of make a theory, break that theory. The standard model is our current working model of how physics, and physicists love the standard model so much that they try and break it constantly. Look, it's the scientific love language. The standard model predicts certain particle behaviors in weird situations. Scientists then put said particles in those situations to see if they behave the way the model would predict. This is how physicists predicted the existence of the Higgs boson decades ahead of the experiments that actually detected it back in 2012. I mean, the standard model said it would be there, and after years and years, we could finally get our experimental setups to the caliber required to test that theory. When everything fits, yay the standard model. When it doesn't, scientists feel a combination of overwhelming excitement and creeping trepidation. Okay, the excitement I get, but why the trepidation? Because, on the one hand, you may have discovered something amazing that breaks the standard model as we know it. But on the other hand, it might be a you problem, and sometimes that's kind of embarrassing. Years ago, when we thought physicists had discovered a faster-than-light neutrino, it turned out to be a loose electrical cable. And on the one hand, you really want to report a finding that meaningfully elaborates on the standard model of freaking physics if your data are telling you that a neutrino is faster than light. On the other hand, as a scientist, you really don't want to publish some big world-changing finding, only to have to retract it in front of all the scientists you respect, and you definitely don't want to retract it because some dust got in your cable housing. That's why, despite the breathless science reporting about a 5th fundamental force this week, this field of physicists have been taking decades to build and confirm these findings. This 5th fundamental force news is follow-up on a story we discussed back in 2021, also from the Fermilab, which in turn was an attempt to replicate findings from a 2001 experiment at Brookhaven. To recap those experiments, particles called muons aren't behaving in the way they're supposed to. Muons are particles that hold a electromagnetic charge like electrons, but they've got about 200 times the mass. They're not a household name of a particle to most of us because muons are unstable and tend to decay pretty quickly. But they're a big deal to physicists because they've got this record of misbehavior. In the 2001 experiment, the Brookhaven team found that muons were more magnetic than the standard model would have predicted, and that's what got this whole ball rolling. After all, the scientific love language says you try to break the theory, and when you do, time to throw the standard model out the window. Well, okay. Hang on a minute. Are we sure this is real and not an electrical cable type of situation? Well, no, we weren't sure, but there are a lot of potential electrical cables, metaphorically speaking. One of them is data analysis, which is what the 2021 version of this experiment was about. researchers masked their own equipment's clock frequency from themselves, so when collecting and analyzing their data, they wouldn't be biased toward a given result. Without knowing that clock frequency, they couldn't know whether their findings supported or broke the standard model. So they had no way to be like, if I math just a little to the left, we'll get a result that breaks the standard model. Or vice versa. Once it was all over and everything was collected and analyzed, the researchers all gathered around an envelope with a secret clock frequency to find out what all their work had actually meant. They opened the envelope, take a quick second to do the math, then they realized muons really did wiggle weirdly, and our physicists were so hype that they genuinely, literally, started jumping up and down. May we all be so thrilled about our work. I know it seems weird to think about having a biased analysis in physics, like, surely the data's the data, right? But analysis often requires a fair amount of judgment, like, is this a data point an outlier or is it for real? And our Fermilab researchers wanted to make sure that they weren't subconsciously nudging their results and setting themselves up for corrections in the comments. Yes, academic journals absolutely have comments, and they are way more brutal than even YouTube could have prepared us for. So, thanks to that 2021 experiment, we know the muons definitely wiggled weirdly, right? The Brookhaven experiment in 2001 found weird wiggles. The Fermilab experiment in 2021 found the same thing in a situation where they couldn't possibly have known what result their data showed, so time to throw the standard model out the window. Well, okay, hang on a minute. Now we know the weird wiggles aren't the result of motivated reasoning in our data analysis, but, well, are we sure we measured the wiggles properly? And that is about what this most recent finding is trying to do. The Fermilab have replicated their findings once again, this time at double the previous precision and with 4 times as much data. Even other physicists in the field, like Chicago scientist Carlos Wagner, are calling that really unprecedented and really impressive, because, well, that's really, 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 really precise, and this kind of jump in precision is really hard to do. Remember, one of the fundamental challenges of experimental physics is figuring out how to test theoretically predicted but wildly hard to measure phenomena. Like so much in life, it's not just the idea, it's the execution, and that is the specialty of experimental physicists. So, if 2001 muons experiment was cool because it found the phenomenon in the first place, and 2021 muon experiment was cool because of the experimental design that allowed for its unbiased analysis, 2023's experiment is cool because the experimental physicists, they executed to perfection, building an absolutely S-tier setup with a more stable beam, better running conditions, and improved knowledge of the magnetic field that makes the muons wobble. That means this experiment lets us be even more confident that we are definitely seeing what we think we're seeing, and this is not a loose cable-style equipment issue. But what does it all mean? A few different possibilities. It's possible that the muon is wiggling weirdly because another force is acting on it than the ones we're already accounting for. And that's why you hear so much, "Oh my god, there's a 5th fundamental force," from science coverage. It's also possible that everything's still operating according to the usual 4 fundamental forces, but there's another player in the game. That is, the muon could be wiggling weirdly because another particle is acting on it, and we don't yet know how to detect that mystery particle. So, if you've heard, "Oh my god, there's a new elementary particle," in science coverage, that's why. Well, I mean, in either case, time to throw the standard model out the window! Yeah! Break out the bubbly science nerds! Or... okay, here's the thing. We know we're seeing what we think we're seeing. We know we analyzed the data properly and didn't subconsciously bias it. So now it's all about whether the data is out of line with what the standard model predicts. And, believe it or not, now we're double checking our math on what the standard model predicts. The experimental physicists absolutely knocked it out of the park with this one, but when that ball sailed right out of the park, it landed in the theoretical physicist's coffee cup right outside the stadium. Apparently, the predictive calculations for what we would expect these muons to do are not totally straightforward. There are at least two different ways of calculating how electrons and positrons collide to produce hadrons, and that matters because we're trying to account for all the relevant particles' behavior before we say some of them are behaving weird. The traditional way of calculating this hadron vacuum polarization has recently come into a bit of dispute after conflicting experimental results, so that traditional calculation method might not work. The other method apparently involves, to quote Science News, mathematically splitting up space-time into a grid to make the calculations. That grid presumably being the lattice in lattice quantum chromodynamics. It's a newer method, and we've only recently been able to math it out. But standard model predictions made that way are more coherent with these muon wiggles. That is, if this calculation is a better representation of the standard model, then maybe these muons don't throw it out the window after all. But seriously, we're doubting the predictions now? We were fine with the predictions up to this moment, so is it suspicious that when the experiment is definitely for sure, we suddenly find some new way to doubt it? You may have heard extraordinary claims require extraordinary evidence, and any finding that disrupts the standard model counts as extraordinary. Of course, physicists don't want to get egg on their face because the loose electrical cable was embarrassing enough for those other folks, so we're going to check every possible source of error is way more niche and way less pithy than the whole extraordinary claims thing, but, you know, you don't want egg on your face. I get it. Still, no matter what, this latest finding is a big deal in particle physics because it is off the experimental physicist's desk. They did their job in every possible way. We know how muons wiggle. We know we're not analyzing it wrong, and now we're quite confident we have not measured it wrong. Whatever's going on, this is not a faster-than-light neutrino, oh whoops, wait, never mind type of finding. Whether the muon's wiggle is weird, or whether it's not, that question's up to the theoretical physicists. What does the standard model predict exactly? And if it doesn't fit the muon's movement, is that because a force is acting on it? Or a particle? No matter what that answer ends up being, the standard model will change to some degree, either by refining how we perform these predictions in this particular sort of way, or by adding a new force or particle in order to account for observations that we don't fully understand. But we know what we saw, and we know it to a degree that's really unprecedented and really impressive. No, I hope the Fermilab physicists are jumping up and down again. Heck, maybe a wiggle too. Just for the muons.